Okay, let's continue. So primary keys, as we are discussing, right? Not only are there keys that enforce uniqueness on that field, but also uh, enforce certain rules on how a record participates in the relationship with some other records, right? Enforcing the fact that some other records can, if they're going to refer to records in in this table, well, that record needs to exist, right? That unique identifier needs to exist. It will fail any inserts or updates that break that rule. Ideally, um, the primary key is represents some real phenomena, some real data, but oftentimes we settle for some artificial key, right? Like a randomly generated unique identifier. So we also we say that that it has no analogous in the real world, right? Like the social security number, right? It's some random number used for nefarious reasons. Now, foreign keys are the other side of the coin of the primary key, and these are fields that are referring to those records, right? Where a section might say that, hey, I'm a section that belongs to a particular course, so I might have a field that has the value of that primary key that I'm referring to, and if I give it a value in this foreign key in this field that has no analogous value on the primary key, then the insert or update or data manipulation will fail, right? And that's what we mean by referential integrity, that the references need to match. Also, other rules that are enforced are that once you have records that are referring to other records, we say that there's a kind of like a parent-child relationship between the two, right? Where a course is the parent, and then you have many sections that are the children, right, that belong to a course. Yes, and all the sections have foreign keys that are referring to the same course. Yes, and so one of the rules that are enforced between primary keys and foreign keys is that you can remove a parent, right, if you have a whole bunch of children that are referring to. Otherwise, you would break the rule that some records are referring to need to be referring to things that exist. Okay, and if you remove the record, then they would be orphans, right? They would be referring to something that doesn't exist. But that's kind of also the same as you have a file system where you have a directory that contains child directories or content that you cannot remove the parent until you remove the children themselves. So again, those kinds of rules are enforced by declaring that certain fields are primary keys and foreign keys. In our case, the students and the courses and the sections already have these types of fields. You have the major ID being a foreign key in the student table that is referring to the department. Is same thing with the course, is also referring to the department. The sections have the course's ID is a foreign key that refers to the primary key in the course, and enrollment has two foreign keys. Right, I think it's referring to a student ID that refers to a student. It also has a foreign key to the section, right, that refers to the saying what student is enrolled in what section. So it has two foreign keys pointing to two different records. The nomenclature that we're going to be using throughout the semester is that we'll use the name of the table followed, representing the schema, right, saying that a table will have the following fields, and where the natural fields, right, the fields that actually contain data, are going to be just plain text, right? So there's the natural fields, right, that refer to presumably real life phenomena, right? Grades and years and professors and titles and names and whatnot. Everything else, the is in bold or italic or both, right? And it's and they have a particular meaning, right? And these are all fields that are specific to the fact that we're using relational databases, right? It's how the relational databases use the nomenclature and of creating relationships between the records. We have the primary keys are bold, italic, and underlined. Foreign keys are just italic and bold. Um, let's see. If well, it's not shown here, but if they're combined right together, they might be in curly brackets. You don't have to memorize this. We'll provide it whenever we have a quiz or anything like that. I'll show the nomenclature again. What are what we, but it's this for the most part it will be like this. Okay, of what is a foreign key, what's a primary key. Another one thing that's missing from here that we'll introduce a little later is that each one of these will be of a specific data type. Right, some of them will be dates, some of them will be strings, numbers, and whatnot. Okay. But usually the kinds of exercises that we'll be working on will be irrelevant what their data types are. Right? We'll be interested just on the structure of the data as opposed to actual data. Also, the relationship that is established by the foreign key and the primary key in databases, it's naturally bidirectional, right? You can use it to navigate between one record and another record by just saying that I want the records in this table that where the certain field or some foreign key is equal to the value of some other primary key in some other table. Okay, and just this equality of the foreign key and the primary key allows me to extract data from both tables at the same time, right? Just by the criteria of these fields being the same. And so we say it's both. It's bidirectional. In that I can it's the same thing to say that a primary key is equal to foreign key, that a foreign key is equal to primary key, right? And you can usually navigate from one record to the other. Now, this is not true when you map these data structures to equivalent object-oriented models, data models, right? For instance, the way you would represent a has a relationship or a one-to-many relationship in for instance courses and sections. Typically, in an object-oriented data model, you might say, well, here's a course class, and then you have an array of sections. Yes? So you have the parent course that contains all the references to all the instances of the sections in that course, right? That belong to that course. And usually the relationship is unidirectional, right? It is the course who knows about the sections that are related to the course. Yes? Usually you don't have, for instance, in the section, in the representation of the section, in your class section, typically you don't have an instance variable that points back to the course, right? It would be it'd be atypical, right? That you would also have two instances pointing to each other, right? Unless you're creating some kind of list or doubly linked lists, right? Where you're creating some kind of data structure that you want to be able to traverse backwards and forwards, then maybe you would have that, right? Referencing each other. But typically, in a normal data model, it would have you in an object-oriented world, you have the parent having references to the children. Make sense? Okay. So it's unidirectional, whereas in a database it's bidirectional, right? You can equate the foreign key with a primary key and whatnot. The other peculiarity in the difference of data modeling in these two worlds is the fact that in a relational database, it is the children who are aware of their parents, right? Notice that the section has references to the course. Right? It is the child who has a reference pointing to the parent. Notice that the parent, the course, has absolutely no idea that it's related to any section. Right? There is no information in the course about any section, correct? But if you go to the equivalent data model in an object-oriented world, it's actually the backward, right? It is the course who has references to its children, right? And the course knows about the section, but the sections don't necessarily know anything about the parents, right? So we'll come back to this later on. Same thing with XML, same thing with JSON. Different data modeling techniques and different even in UML as well. When we got to the conceptual data model, we'll see that there are some gaps, right, of representing the same exact piece of data, right? But it needs to be structured, because of the idiosyncrasies of each one of these two different worlds, and that's one of the challenges that we'll have to face when we try to convert one to the other, which is a very common thing that needs to be done, right? You're sending JSON from some web UI, right? In Java, running JavaScript sends JSON. JSON needs to be converted into a Java object. That Java object needs to be converted into some, relational database record, right? So you have three different representations of the same exact data, one represented in JSON, then in Java, and then a relational database, right? So all that conversion, right, generates a lot of friction, right, between these different architectures, between all these different infrastructure, and certainly we'll talk about that a little later. Referential integrity is what I was mentioning earlier, that certain rules that you ask the database to enforce for you so that it keeps you from inserting or updating or deleting data, right, that might introduce inconsistency, right, or might make certain records orphaned, referring to things that don't exist, right? By asking the database and tagging certain fields as primary keys or foreign keys that enforce these constraints. So here's, for instance, one existing constraint is that you have two students referring to the department. It would make no sense that the students might refer to a department that doesn't exist. So the database will stop me from either modifying this or inserting a record that have values here that don't match an equivalent record, or would stop me from modifying the value here, or even removing the record, right? Now there are other certain constraints of for instance, if I'm removing something, right? If I'm removing a record from here, or if I'm removing a record from there, how should that be interpreted? In some cases, it might make sense. Yes.
If we have also like null data, and if, like for example, if we're missing one of the fields, could that be also like an enforcing referential integrity? Like if you don't have
Which
like
one is null?
like
This could be null.
yeah.
Yeah, not here.
Okay, but like for example, if we don't have the year of the student, can that be like or
Well, when we say referential integrity, we're only referring to foreign key primary key, when they're referencing each other, right? In the year case, right, it's not referencing anything, right? Um, or it might be, right. You might have a record of all the years, right, and they're referring to those years, right? Or semesters, for instance, you might have records of semesters, fall 2019 or whatever, right? And those might be a record. So and then you might be referring to a record of that refers to some range or some season or something that many folks might be referencing to. Then in that case, yes, it might be enforcing certain referential integrity constraints. Yep. Uh, Yeah, so a little later, we might enforce other rules where it might be okay to remove uh, a record, right? You might say, well, I know that you're going to stop me from removing that. That's the default behavior, but in some cases, it might make sense, right? That I do remove, and what should happen. So would it make sense, for instance, that if I remove the math record, right? How should that propagate, right? So, for instance, if this were two orders, right, and this were a product, right, and the product is no longer being sold, but there are orders, it might make sense that if I remove the product, right, that could cascade down to removing the orders, right? Because it might make no sense to keep around the orders if the product doesn't exist anymore, right? And so heuristically, we might decide to enforce that kind of rule, and the database can help us do that. If you remove the parent, yes, you should cascade that to removing the children, right? But in this case, for instance, it might make no sense, right? That if I remove the department, should I also remove the students? Right? That might make no sense, right? And so it's great that it's stopping me from doing that. Yeah. Or it might be that if the rules might be that if I remove the parent, then I can set the children to be null, meaning they're not referring to any record because I don't know what the records are, right? Or setting it to a specific value, right? If I remove from computer engineering, then now all the students are in computer science college, right? So I might automatically switch them over to some other department. Yes. So all those kinds of things that we can configure the database to help us, right? Enforce these kinds of rules for us, and it's all encompassing what we mean by enforcing referential integrity, right? On what to do with these things that are referring to each other. So yeah, this is what I meant by the cascade actions that we can enforce. That if certain records that participate in the relationships, cascade or propagate over to those other records that are related to the to those records. Cascade actions might be that you can change a value, like change from computer engineering to computer science, right? If all of a sudden a particular department goes away, what do you do with all these students? They might become orphans, meaning they don't point to anything, and maybe that makes sense. Now they're unmatriculated or they're not registered anywhere, and somebody has to make a decision on where they're gonna go on change or update and cascade those going forward. Other so these constraints are all a set of family of constraints or rules that the database can help us, right? For instance, might say that this has to be a string, or this has to be a date, or this has to be a number, right? It has to be. Those are all sorts of constraints that we ask the database to enforce for us, just like you would declare in Java a strongly typed. You would use a strongly typed language, right? That would make sure that we are providing with good data, as opposed to JavaScript that is a not a strongly typed language and everything is debugged at runtime. What you want to do is catch these errors as early as possible, right, before going out to production, right? Strongly typed languages, strongly typed databases, plus all sorts of rules, right? They cannot be null, right? And it could enforce things such as required fields, right? You can't register unless you give me an email, right? You need to give me a password. Those are required. It can't be null, right? Or key constraints, referential constraints, data types constraints, all sorts of constraints. All right, so let's talk about SQL. So SQL is the language they're going to be using for the next month and a half or so. Yes. We'll do it in SQL in a minute. Yes, where you declare a variable and you say whether it's an int, double, date, varchar, whatnot. Those are data type constraints. And also you can prepend it with keywords such as primary, or whether it's this is a foreign key that is referring to this primary key in that other table. We'll do that now. So yeah, so SQL is the language, structured query language, is the language that we're going to be using for the next 2 months, perhaps. That will allow us to interact with the database, right? It's there was an effort to make it look like English as much as possible, to lower the bar of entry for folks that might find it easy to be able to interact with what was considered fairly complex back several decades ago. Today it's perhaps unfortunate that it's too English-like, that it's perhaps not more programmatic, perhaps. Anyway, so the first statements that we're going to be exploring is the create table statement, right? That will allow us to declare the schema, right, and creating all these buckets of data that will allow us to declare the name of the table, what the fields and the various constraints for within that table. You can declare all sorts of data types, but then all the constraints on what happens when it's deleting, or what happens if it's updating, or verify that the year that I'm graduating is after 18 something. That the school was founded. But it makes no sense that I'm graduating before the school was established, right? So there's all sorts of constraints, and you can put regular expressions. You can put all sorts of validation that you can put on data types and certain fields, and we'll look at that as well. So here's our most simple department table. So create table department, department ID, department name, and so those are the two fields, right? Department ID and department name. Everything else is constrained, right? So the department ID has to be an integer, and it cannot be null. It cannot be null. So that is required. Then the department name needs to be a string of 10 characters long, and as maximum 10 characters long. It's also required, not null. And then we're declaring the department ID as a primary key, right? So it's a key, so it has to be unique. And it's primary, meaning that if I have somewhere else a foreign key, I'm going to enforce the referential integrity rules, right? If you have somebody referring to you, you cannot remove the record, right? If nobody's referring to you, it's okay. You can remove the record, okay? So I'm going to enforce all those rules. So plus here is the student, right? So I have a student ID. It cannot be null, so it's required. Student name, it's a string. It can't be null. It's required. Department. Presumably it's going to be a foreign key. It's referring to the department. Also, it's requiring it's in an integer. Graduating year, the only constraint here is that it's an integer. Presumably, we could have added the fact that the year needs to be positive. It can't be negative or something like that. Or that it should have been. Oh, actually, no, we do. Here we have a constraint. Validate that the year is greater than 1863. Other things here is you can every field you can enforce default values. In strings you can select an initial value for the string or initial value for the graduation year. Meaning if the value is not provided, then we'll choose the default value. For instance, created on and updated on is very common. That we want to keep track of a log or an audit, when this record was last updated or when it was initially created. So we can say, well, it's a timestamp. The default value is the current timestamp, meaning when the record was created. I'll look at the clock, the current, and I'll use that as the initial value. Updated on, we have it has an on update constraint, meaning when this record modifies, when this record is ever updated, I want to update the value of this field to be the current timestamp. So I'll always keep track of when was the last time this record was modified. It won't keep a history, right? It'll only just keep a record when was the last time that was modified. We could have additional triggers and things like that could keep a history, like an audit, right, of whenever a record was modified. Who modified it, when was it modified, what was before and after. So we'll look at triggers a little later that can listen for changes in records, and then and do certain logic and run certain algorithms. We're saying that our student ID is a primary key, meaning if anybody refers to us, we're going to enforce referential integrity. We're saying that the department field is a foreign key that is referencing some other table, and that table has a primary key, presumably, which is the department ID, plus all sorts of other constraints, meaning if it's removed, meaning if the department ID is removed, I want to know about it, right? I'm going to be removed, or update, right? If the department changes from 20 to 21, then I want to know. I want it to be changed as well, right? The department change, I want to be changed as well, and some validation that the SID has to be positive and the graduation year has to be after the year that the department was created. A couple more. Here's a course with its primary key, course ID. Title is a string. Also, it's a good practice to add a comment that describes the field, right? Usually, some business logic or some business rule definition would be added there as a comment, a description. One thing that it's not quite kosher here. Notice the grad year is using camel case, right? In SQL, there is no enforcement of the casing, right? So usually we use underscores instead, right? So grad underscore year would be a more valid name for that, or created underscore on. Although, later on we would look at mapping, object-oriented, classes to these databases, right? Schemas. Oftentimes the naming conventions are different, right? So in Java you do use camel casing, right? Whereas here it's all underscore. So how do you bridge that gap, right? And we'll see how ORMs can be configured, right, to do that kind of mapping in the differences in naming conventions. Same thing, primary key, foreign key, referring to one another, and that's it, right? Okay, any questions?